Take a moment to settle into your bed. Feel the weight of your body pressing gently against the mattress. Close your eyes and allow the quiet to expand around you, the subtle rhythm of your breathing marking the passage of time. Imagine the vastness beyond your window, a quiet space stretching infinitely, and let your mind drift toward distant places, far beyond Earth, where even the air carries mysteries beyond our ordinary senses. Tonight, we will journey to one such place, a world whose name evokes curiosity, humor, and a peculiar chemical reality: Uranus. Why does Uranus smell the way it does? That question, simple yet striking, opens a door into the unseen chemistry of a distant planet. Uranus is not just another celestial body orbiting our sun. It is a dynamic world with an atmosphere layered in clouds and gases, each contributing to an environment unlike anything experienced on Earth. Its position as the seventh planet from the Sun places it in a realm of extreme cold, where temperatures can drop to nearly minus 224 degrees Celsius, colder than any other planet in our solar system. Despite this frigid environment, Uranus is alive with chemical activity, its gaseous envelope composed of elements that produce effects both surprising and detectable by our instruments, if not by our noses directly. Uranus is often called an ice giant, and this designation points toward the substantial quantities of volatile substances it contains, rather than implying frozen water at its cloud tops. Hydrogen and helium dominate its composition, forming more than 99% of the atmospheric gases. These primary constituents are relatively inert and colorless, forming a thick, transparent medium through which sunlight filters weakly, imparting the pale blue-green hue that gives Uranus its serene appearance. Yet hidden within this vast envelope of hydrogen and helium are trace molecules that define the planet's unique character, including methane, ammonia, and crucially, hydrogen sulfide. It is hydrogen sulfide, a compound known on Earth for its unmistakable scent of rotten eggs, that gives Uranus the hypothetical odor for which it has become famous in popular imagination. Hydrogen sulfide is chemically simple, consisting of two hydrogen atoms bound to a sulfur atom. Yet its presence within Uranus's atmosphere is far from trivial. The molecule's volatility and reactive properties mean that it tends to accumulate in particular layers of the atmosphere, especially the colder, deeper regions, where pressures are several times that of Earth's atmosphere at sea level. Here, hydrogen sulfide exists as a gas under extreme conditions that challenge our earthbound understanding of chemistry. Above these depths, the gas mixes with methane and other trace compounds, forming a layered structure of clouds that rise and fall with the planet's turbulent winds. The atmosphere of Uranus is divided into distinct layers, each characterized by temperature, pressure, and composition. The outermost layer, the exosphere, gradually transitions into space and is extremely thin, containing mostly hydrogen and helium. Beneath this, the thermosphere experiences heating from ultraviolet radiation and charged particles, while the stratosphere contains a more stable mixture of gases. It is within the troposphere, the lowest layer of the atmosphere, where convection currents are active, that hydrogen sulfide is most concentrated. Here, the interplay of rising and sinking air masses drives chemical mixing, spreading the gas through the cloud layers and influencing the planet's weather patterns, which are less visible than Jupiter's storm bands, but no less dynamic. Observational evidence of hydrogen sulfide on Uranus came initially from spectroscopic analysis. Scientists measure the absorption of specific wavelengths of light as they pass through a planet's atmosphere. Each molecule absorbs light at distinct frequencies, creating a spectral fingerprint that can be detected even across vast distances. For Uranus, spectral lines corresponding to H2S confirmed its presence, revealing that the gas dominates certain layers above the planet's cloud deck. These findings were complemented by measurements from Voyager 2, which flew past Uranus in 1986, providing direct data on atmospheric composition, temperature, and pressure. The probe's instruments detected variations in methane and other hydrocarbons, while indirect evidence of hydrogen sulfide further supported the conclusion that Uranus's atmosphere contains a significant concentration of sulfur-bearing compounds. The temperature and pressure conditions within Uranus's troposphere are extreme by terrestrial standards. At pressures several times that of Earth's atmosphere, hydrogen sulfide behaves differently than it does near our surface, remaining gaseous despite the intense cold. Methane, in contrast, condenses at higher altitudes, creating faint blue-green clouds that drift in patterns shaped by the planet's unique axial tilt. Uranus rotates on an axis tilted approximately 98 degrees relative to its orbital plane, essentially rolling along its orbit. This tilt results in unusual seasonal cycles, with each pole experiencing decades of continuous sunlight or darkness, further affecting atmospheric circulation and the vertical distribution of gases like hydrogen sulfide. In comparison to its neighbor Neptune, Uranus presents a distinct chemical environment. Both planets share similar bulk compositions, yet Uranus appears less vibrant in atmospheric activity, with weaker cloud formations and storm activity. Nevertheless, the presence of hydrogen sulfide is more pronounced on Uranus, giving it a theoretical olfactory distinction. Jupiter and Saturn, though richer in hydrogen and helium and hosting ammonia clouds, contain far less hydrogen sulfide near their observable cloud tops, which explains why Uranus alone can claim this peculiar chemical identity. These scientific insights not only satisfy curiosity about planetary smells, but also inform broader understanding of planetary formation. The prevalence of hydrogen sulfide points to the materials available in the protoplanetary disk during Uranus's formation, suggesting that sulfur-bearing compounds were abundant in its region of the early solar system. Studying these distributions helps scientists model how ice giants acquire their atmospheres, offering parallels to exoplanets found in distant star systems. The simple chemical signature of hydrogen sulfide thus becomes a key to unlocking complex histories of planetary chemistry and evolution. Even without ever breathing its air, we can imagine the sensory reality of Uranus through careful study. Hydrogen sulfide is toxic to humans and lethal in concentrated form, yet on a distant ice giant, it exists in a vast, uninhabited expanse carried silently by cold winds that swirl around invisible cloud formations. The thought that a planet can have a defining smell, one that resonates with earthly associations of decay, is a quiet reminder of how varied and extreme the universe is, how chemistry shapes worlds in ways both beautiful and strange. Each molecule in Uranus's atmosphere participates in a delicate balance of physics and chemistry, contributing to the alien landscape of a world far removed from human experience, yet deeply knowable through careful observation. Above the visible cloud layers, Uranus's troposphere gradually transitions into the stratosphere, where temperatures rise slightly due to absorption of ultraviolet radiation by methane and other trace gases. In this region, hydrogen sulfide becomes more diffuse, its molecules mingling with methane, ethane, and minor hydrocarbons. Spectroscopic studies reveal subtle variations in gas concentrations across latitudes, hinting at a complex interplay of atmospheric dynamics. Winds, though less intense than those on Neptune, can reach speeds of up to 900 kilometers per hour, sweeping hydrogen sulfide and other gases along curved trajectories that trace the planet's rotation and axial tilt. These currents form invisible rivers in the sky, guiding the movement of chemical clouds without revealing their paths to the eye. The formation of Uranus's hydrogen sulfide-rich atmosphere is a story that begins billions of years ago in the swirling disk of gas and dust that surrounded the young sun. As materials collided and coalesced, heavier compounds, including sulfur, migrated toward forming ice giants. Unlike the terrestrial planets, where gravity pulled dense rock toward the core, Uranus accumulated volatiles in its outer layers, locking hydrogen sulfide into the expanding atmosphere. The result is a composition unlike anything on Earth, with sulfur compounds suspended in a sea of hydrogen and helium, creating a gaseous world where chemistry operates on scales and pressures unimaginable on our home planet. Temperature gradients play a critical role in the behavior of hydrogen sulfide. Near the cloud tops, temperatures hover around -224 degrees Celsius, causing the gas to condense into faint hazes in some layers. Deeper down, where pressure increases to several tens of bars, hydrogen sulfide remains gaseous, its molecules compressed yet still capable of movement. These gradients define the vertical structure of the atmosphere and influence cloud formation, with methane clouds forming above regions where hydrogen sulfide is most concentrated. The slow, methodical rise and fall of air masses distributes these gases horizontally, spreading the compounds across latitudes and creating a subtle layering effect that remains consistent over decades. Uranus's magnetic field adds another layer of complexity to its chemical environment. The field is tilted relative to the rotation axis by approximately 59 degrees, producing a magnetosphere that interacts with charged particles from the solar wind in unusual patterns. These interactions can energize upper atmospheric particles, creating auroras that shift and pulse over the poles. While hydrogen sulfide resides primarily in the lower troposphere, the magnetic environment indirectly affects its distribution by influencing atmospheric circulation patterns. Charged particle precipitation can drive chemical reactions in higher layers, producing secondary molecules that gradually settle downward, further enriching the lower atmosphere with sulfur compounds. Detection of hydrogen sulfide relies heavily on remote sensing techniques. Infrared spectroscopy captures the absorption features of H2S, revealing concentrations even from Earth-based telescopes. These measurements require careful calibration to account for overlapping spectral lines from methane and ammonia, which can obscure or mimic hydrogen sulfide signatures. By analyzing subtle differences in absorption wavelengths, scientists map the vertical and horizontal distribution of H2S, constructing models that predict its behavior under varying temperature and pressure conditions. These models are cross-referenced with data from Voyager 2, whose instruments provided snapshots of atmospheric composition and thermal profiles during its brief flyby, confirming the presence of sulfur-bearing molecules in regions where the instruments could detect them. Compared to other gas and ice giants, Uranus's hydrogen sulfide content is distinctive. Jupiter's atmosphere is dominated by hydrogen and helium, with clouds of ammonia ice, while sulfur compounds exist deeper down, shielded by thick ammonia and water layers. Saturn exhibits a similar pattern, with sulfur present, but largely obscured. Neptune, although similar in size and composition to Uranus, shows weaker signatures of hydrogen sulfide in its upper atmosphere. This contrast highlights the unique chemical environment of Uranus and raises questions about the precise processes that concentrated H2S in its troposphere. Planetary scientists infer that slight variations in formation conditions, temperature gradients, and convective mixing can lead to measurable differences in gas distribution, demonstrating the delicate interplay of factors shaping planetary atmospheres. Hydrogen sulfide's physical properties also influence its atmospheric behavior. The gas is denser than hydrogen, but lighter than water vapor, allowing it to remain suspended in turbulent layers while slowly diffusing toward equilibrium. Its interactions with methane and ammonia create faint chemical clouds, whose appearance is largely invisible but detectable through spectroscopy. Over time, ultraviolet light from the sun breaks down some molecules in the upper atmosphere, initiating photochemical reactions that produce more complex sulfur-containing compounds. These secondary molecules gradually settle, enriching the troposphere and contributing to the persistent presence of H2S over the planet's long seasonal cycles. Seasonal changes on Uranus unfold over decades due to its 84-year orbital period and extreme axial tilt. During each long summer and winter, one pole remains in near constant sunlight or darkness for approximately 42 years. This prolonged exposure affects atmospheric chemistry, altering temperature gradients, convection patterns, and gas distribution. Hydrogen sulfide molecules may rise slightly during warmer periods and sink during colder intervals, but the overall structure of the troposphere remains stable. This slow rhythm of atmospheric change contrasts sharply with Earth's rapid seasonal cycles, emphasizing the patience required to study such distant worlds. As observers, we rely on indirect evidence to reconstruct Uranus's chemical profile. Photometric analysis, infrared imaging, and spectroscopy collectively reveal the concentration of hydrogen sulfide and its interaction with other gases. Laboratory experiments on Earth simulate these conditions, studying H2S under low temperatures and high pressures to predict behavior on Uranus. Such experiments confirm that hydrogen sulfide remains gaseous under deep atmospheric pressures, condenses only under extreme cooling, and can interact with methane to form minor hazes or clouds. These findings provide a window into reality impossible to experience directly, allowing scientists to smell Uranus in the laboratory through measurement, rather than sensation. The presence of hydrogen sulfide also informs our understanding of planetary habitability and chemical diversity. While Uranus itself is inhospitable, the chemistry within its atmosphere demonstrates the range of conditions under which sulfur compounds can exist. These insights have implications for studying exoplanets, where similar molecules might appear in diverse environments. Recognizing hydrogen sulfide on distant worlds helps define criteria for atmospheric composition, chemical stability, and planetary evolution, offering a benchmark against which new discoveries can be measured. Even without physical contact, Imagining Uranus's hydrogen sulfide-rich atmosphere evokes a sensory awareness that is uniquely scientific. We understand the compound's odor on Earth, yet here it is suspended in a frigid, turbulent environment, forming layers of invisible chemistry that drift silently across the planet. These molecules are carried by winds, stirred by convection, and subtly altered by photochemical reactions, creating an environment that is simultaneously alien and comprehensible. Each layer, each molecule, each interaction contributes to the intricate dance of planetary chemistry, offering a quiet but profound insight into the diversity of worlds beyond our own. Delving deeper into Uranus's atmosphere, we find that the distribution of hydrogen sulfide is not uniform, but shaped by subtle variations in temperature and pressure. In the lower troposphere, where pressure can reach tens of bars, H2S remains gaseous despite the extreme cold. Convection currents slowly carry it upward, where temperatures drop further, causing slight condensation into faint, invisible hazes. These hazes interact with methane clouds, creating layers that are discernible only through careful spectroscopic observation. The balance between rising warm air and descending cooler air defines the vertical movement of gases, ensuring that hydrogen sulfide is continuously circulated throughout significant portions of the atmosphere. Uranus's axial tilt of approximately 98 degrees dramatically influences atmospheric behavior. Unlike planets with moderate tilts, Uranus experiences prolonged periods in which one pole faces the sun continuously, while the opposite pole remains in darkness. During the sunlit decades, heating of the upper atmosphere affects chemical reactions, allowing photodissociation of some methane molecules and contributing to the formation of secondary sulfur compounds. These reactions subtly enrich lower layers of the atmosphere, reinforcing the presence of hydrogen sulfide over long timescales. When the dark pole rotates into sunlight, similar processes occur in reverse, creating a slow, planetary-scale rhythm of chemical flux. Winds on Uranus, though less visually striking than Jupiter's, play a significant role in moving hydrogen sulfide across the planet. High-latitude regions exhibit faster east-west winds that sweep molecules along curved paths, while equatorial regions experience slower, more uniform flows. The combination of rotation and axial tilt produces complex circulation patterns, ensuring that H2S and other trace gases are mixed horizontally as well as vertically. These currents distribute gases into layers that extend across thousands of kilometers, maintaining the overall chemical equilibrium and contributing to the planet's subtle color variations, which are influenced by the presence of methane and hydrogen sulfide together. Spectroscopy remains the key to understanding Uranus's chemical environment. By measuring absorption lines at precise wavelengths, astronomers can identify the unique signature of H2S amidst a background of hydrogen, helium, and methane. Instruments on Earth-based telescopes capture infrared light absorbed by these molecules, allowing researchers to determine concentrations at varying altitudes. The Voyager 2 flyby supplemented this information, providing thermal profiles and direct measurements of cloud composition. By combining these datasets, scientists construct detailed models of Uranus's atmospheric chemistry, predicting the behavior of hydrogen sulfide in relation to other gases under extreme temperatures and pressures. The behavior of hydrogen sulfide in Uranus's atmosphere offers insight into the planet's formation history. During the early solar system, sulfur compounds were abundant in the region where Uranus formed. As the planet accreted, volatile substances including H2S were trapped in its outer layers. The gas's current distribution reflects both initial concentrations and ongoing atmospheric dynamics. Comparisons with Neptune suggest that even small differences in formation conditions, such as local temperature or density variations in the protoplanetary disk, can lead to measurable differences in atmospheric composition, illustrating the sensitivity of planetary chemistry to initial conditions. Chemical interactions further enrich Uranus's atmospheric complexity. Ultraviolet radiation from the Sun can break down H2S molecules in the upper layers, producing elemental sulfur and minor sulfur-bearing compounds. These particles gradually settle into lower layers, reinforcing the concentration of hydrogen sulfide in the troposphere. Methane participates in photochemical reactions as well, forming ethane and other hydrocarbons that interact with sulfur compounds. This slow, continuous cycle of photochemistry, vertical mixing, and diffusion shapes the chemical landscape of the planet, creating a dynamic yet stable environment in which hydrogen sulfide persists over decades and centuries. Temperature gradients within the atmosphere are crucial to the stability of hydrogen sulfide. At higher altitudes, low pressure and extreme cold reduce molecular movement, causing minor condensation into hazes. Deeper down, high pressure keeps H2S in gaseous form, while methane condenses into faint blue-green clouds. These layers drift slowly under the influence of planetary rotation and convection currents. The result is a stratified atmosphere where hydrogen sulfide is concentrated in mid to lower troposphere levels, surrounded by layers of methane, ammonia, and other trace gases that together define the chemical signature of Uranus. Comparing Uranus to its planetary neighbors provides context for understanding its chemical uniqueness. Jupiter's deep atmosphere contains sulfur, but it is obscured beneath ammonia and water clouds. Saturn exhibits a similar pattern, with sulfur compounds less prominent in the upper layers. Neptune, while similar to Uranus in mass and composition, shows weaker hydrogen sulfide signals, suggesting either lower initial abundance or more efficient chemical sequestration. This contrast highlights the importance of detailed chemical observations in understanding planetary formation and evolution, and underscores why Uranus stands out for its distinctive sulfur content. Laboratory studies on Earth help interpret Uranus's chemical behavior. Scientists recreate low-temperature, high-pressure environments to study how H2S behaves alongside methane and other gases. These experiments confirm that hydrogen sulfide remains gaseous under extreme pressures, condenses under additional cooling, and participates in minor photochemical reactions when exposed to ultraviolet radiation. Such controlled studies allow researchers to predict atmospheric dynamics on Uranus with higher accuracy, bridging the gap between remote sensing data and the physical reality of the planet's environment. Through these observations, we gain a sense of Uranus as a chemically active world, where hydrogen sulfide circulates quietly yet persistently. The gas defines a subtle but critical aspect of the planet's identity, giving it an olfactory character that, if experienced directly, would be starkly pungent. Even without physical presence, understanding the role of hydrogen sulfide allows us to appreciate the diversity of planetary chemistry, reminding us that every world carries signatures of its formation history, its environment, and the complex interplay of physics and chemistry that shapes its atmosphere. As we move further into Uranus's atmosphere, the delicate balance of gases becomes increasingly evident. Hydrogen sulfide, though invisible, plays a central role in defining the chemical architecture of the planet. In the lower troposphere, where pressure reaches levels dozens of times greater than Earth's atmosphere, H2S coexists with hydrogen, helium, and methane in a tenuous equilibrium. Convection gently lifts parcels of air, carrying the gas upward toward cooler altitudes where minor condensation may occur, forming thin, diffuse hazes. These layers, imperceptible to the naked eye, influence the planet's spectral characteristics, subtly shaping the blue-green hue captured by distant telescopes. Hydrogen sulfide's interaction with methane creates a chemical layering that is both vertical and latitudinal. In mid-latitudes, where solar heating is moderate over Uranus's decades-long seasons, convection and wind patterns distribute gases horizontally. The rapid east-west winds at high latitudes accelerate this mixing, ensuring that H2S concentrations remain relatively consistent across broad swaths of the planet. Despite the extreme cold, the gas maintains mobility within the atmosphere, diffusing slowly in response to temperature, gradients, pressure differentials, and the Coriolis effect induced by the planet's rotation. Uranus's magnetic field adds subtle complexity to these dynamics. Tilted far from the rotational axis, it produces magnetospheric interactions that influence charged particles in the upper atmosphere. While hydrogen sulfide resides mainly in the lower layers, charged particles descending from higher altitudes can instigate photochemical reactions that alter trace gases, producing secondary sulfur compounds. These molecules gradually settle, enriching the troposphere and subtly affecting the overall chemical balance. The magnetic environment, in conjunction with long seasonal cycles, ensures that the distribution of H2S is both dynamic and resilient over time. Spectroscopic observations from Earth and space remain crucial for understanding these patterns. Each molecule absorbs light at precise wavelengths, providing a spectral fingerprint that reveals its abundance and location. By comparing absorption features from multiple wavelengths, scientists can distinguish hydrogen sulfide from methane, ammonia, and other compounds. Infrared measurements, in particular, capture H2S signatures in the mid and lower atmosphere, while ultraviolet and radio observations provide complementary insights into temperature profiles and cloud distributions. Voyager 2's instruments offered the first in situ confirmation of these gases, validating the remote observations and providing data for atmospheric models that continue to refine our understanding. Hydrogen sulfide's behavior under Uranus's extreme conditions is shaped by both physical and chemical forces. At higher altitudes, cold temperatures reduce molecular movement, causing a fraction of H2S to condense into fine particles. Deeper within the atmosphere, increased pressure keeps the gas in a stable, gaseous state. This stratification is reinforced by convection, with warm parcels rising and cooler parcels descending, producing a subtle but continuous vertical mixing. Methane clouds form slightly higher in the troposphere, creating layers that overlap with hydrogen sulfide, adding to the complexity of Uranus's atmospheric structure. The distribution of hydrogen sulfide offers clues about the planet's formation. During the early stages of the solar system, sulfur-rich compounds were abundant in the region where Uranus coalesced. Accretion trapped these volatiles in the outer layers of the growing planet. Over billions of years, convection, diffusion, and photochemistry have maintained H2S in the troposphere, creating a chemical fingerprint that preserves evidence of its primordial environment. In contrast, Neptune, formed in a similar region, exhibits less hydrogen sulfide in its observable atmosphere, indicating that even minor variations in initial conditions can produce distinct chemical profiles in ice giants. Photochemical reactions in Uranus's upper atmosphere contribute to the persistence of hydrogen sulfide. Ultraviolet radiation breaks down H2S molecules, generating elemental sulfur and minor sulfur-bearing compounds. These particles gradually settle toward lower layers, supplementing the existing H2S concentration. Methane participates in parallel photochemistry, forming ethane and other hydrocarbons that interact with sulfur compounds, producing faint hazes that can be detected spectroscopically. This ongoing chemical cycling underscores the dynamic nature of Uranus's atmosphere, where even an apparently inert environment experiences continuous transformation. The slow, measured pace of chemical redistribution on Uranus contrasts with the rapid cycles on Earth. Seasonal shifts unfold over decades, influencing temperature gradients and convection patterns, which in turn affect the vertical and horizontal movement of hydrogen sulfide. The long orbital period, combined with extreme axial tilt, ensures that atmospheric conditions evolve gradually, allowing for stable, layered distributions of gases. Understanding these patterns provides insight not only into Uranus's current atmosphere, but also into the processes that govern ice giants throughout the galaxy. Laboratory experiments on Earth simulate these extraterrestrial conditions to better understand H2S behavior. Scientists recreate low temperatures and high pressures, observing gas mobility, condensation points, and chemical interactions with methane and ammonia. Ultraviolet irradiation tests replicate photochemical reactions that occur on Uranus, confirming that hydrogen sulfide persists in the troposphere despite ongoing breakdown in upper layers. These controlled studies provide a bridge between observational data and theoretical models, enabling precise predictions about the gas's behavior under a range of planetary conditions. Even without a physical presence on Uranus, we can sense the chemical reality of hydrogen sulfide through these methods. The gas defines a distinct component of the planet's identity, invisible yet measurable, shaping the color, structure, and chemical balance of the atmosphere. Each molecule participates in a complex network of physical and chemical interactions, moving along convective currents, interacting with ultraviolet radiation, and contributing to the layered dynamic structure of Uranus's troposphere. The planet, in its quiet extremity, offers a window into the richness of chemical processes that define worlds far beyond human experience. The chemical signature of Uranus extends beyond hydrogen sulfide, yet H2S remains the defining contributor to the planet's olfactory identity, at least in theoretical terms. Minor gases such as ammonia and methane participate in the atmospheric composition, but their presence does not replicate the distinct sulfurous character imparted by H2S. Ammonia, though volatile, exists in lower concentrations and primarily interacts with water ice deep in the planet's interior, while methane dominates the upper troposphere, giving Uranus its characteristic blue-green coloration. The layering of methane above hydrogen sulfide is critical, As sunlight filters through the methane-rich upper atmosphere, it indirectly illuminates the presence of underlying H2S, which shapes the spectral absorption patterns that telescopes detect across vast interplanetary distances. Within the troposphere, the interaction of hydrogen sulfide with methane and trace hydrocarbons contributes to subtle cloud formation. These clouds are faint, often invisible to optical telescopes, yet they create measurable opacity in specific infrared wavelengths. As parcels of air rise and cool, H2S can partially condense, forming thin, dispersed hazes that float gently in the slowly circulating atmosphere. These processes, while imperceptible to direct observation, are critical for understanding the vertical structure and chemical layering of Uranus, providing indirect confirmation of H2S distribution patterns and reinforcing models based on Voyager 2 data and ground-based spectroscopy. The motion of gases within Uranus's atmosphere is slow but consistent. Convection transports hydrogen sulfide upward in warm currents and downward in cooler, denser air. Wind speeds vary with latitude and altitude, with high-latitude jets reaching speeds approaching 900 kilometers per hour. These winds carry H2S horizontally, redistributing sulfur compounds across thousands of kilometers. Despite the immense scale, these processes occur gradually, shaping an atmosphere that is chemically uniform on a planetary scale, yet dynamic in local variations. Uranus's extreme axial tilt, nearly parallel to its orbital plane, produces decades-long seasons that influence the chemical and physical properties of the atmosphere. Each pole experiences continuous sunlight or darkness for approximately 42 Earth years. Prolonged exposure to sunlight enables photochemical reactions that break down hydrogen sulfide in upper layers, forming elemental sulfur and minor compounds that eventually descend, enriching lower layers. During the dark seasons, the absence of ultraviolet radiation slows these reactions, allowing H2S concentrations to stabilize. This cyclical process contributes to the long-term persistence of hydrogen sulfide in the troposphere, maintaining the planet's characteristic chemical signature over centuries. Laboratory simulations on Earth reinforce our understanding of these processes. Experiments conducted at low temperatures and high pressures replicate the conditions found within Uranus's atmosphere, allowing researchers to observe hydrogen sulfide behavior directly. These studies confirm that H2S remains gaseous under tropospheric pressures, condenses only under extreme cooling, and participates in slow photochemical reactions when exposed to ultraviolet light. By measuring the gas's physical and chemical properties under controlled conditions, scientists refine atmospheric models, improving predictions of chemical layering, vertical distribution, and seasonal variation. Spectroscopy continues to reveal the intricacies of Uranus's atmosphere. Infrared absorption lines identify the presence of hydrogen sulfide at specific altitudes, while ultraviolet and radio measurements provide complementary data on temperature, pressure, and cloud distribution. These observations, combined with historical Voyager 2 data, allow researchers to construct detailed profiles of the planet's atmospheric composition. Each spectral line, each absorption feature, corresponds to a molecule of hydrogen sulfide, giving scientists a precise understanding of its concentration and distribution even without direct sampling. Comparisons with other planets illustrate the uniqueness of Uranus's chemical environment. Jupiter and Saturn, with abundant hydrogen and helium, contains sulfur compounds primarily in deeper layers, shielded by ammonia and water clouds. Neptune, though similar in size and composition, exhibits weaker H2S signals in its upper atmosphere. Uranus, by contrast, demonstrates significant hydrogen sulfide presence in observable layers, creating a chemical signature distinct from any other planet in the solar system. These differences highlight the subtle variations in formation conditions and atmospheric dynamics that define each ice giant. The chemical cycling of hydrogen sulfide is both persistent and dynamic. Ultraviolet radiation breaks down some H2S molecules in upper layers, generating secondary sulfur compounds that settle into the troposphere. Convection and diffusion continuously redistribute the gas, ensuring stability despite ongoing photochemical reactions. Methane and trace hydrocarbons participate in parallel reactions, forming ethane and other minor molecules that interact with sulfur compounds, creating faint hazes detectable through infrared spectroscopy. This interplay of processes maintains the atmosphere's chemical equilibrium, demonstrating the resilience of hydrogen sulfide under extreme conditions. Temperature gradients within the atmosphere further influence hydrogen sulfide's behavior. The upper troposphere, exposed to extreme cold, allows partial condensation of the gas into thin hazes. Deeper layers, subject to high pressure, maintain H2S in gaseous form. These gradients, combined with wind patterns and axial tilt effects, create a complex, multi-layered structure in which hydrogen sulfide persists over long timescales. The chemical stability and vertical distribution of H2S serve as markers for understanding the formation, evolution, and ongoing dynamics of Uranus's atmosphere. Even without the ability to smell the gas directly, we can imagine the effect of hydrogen sulfide on Uranus. The planet's invisible, sulfur-rich atmosphere drifts silently, shaped by slow winds, convection, and photochemistry. Each molecule contributes to a vast, dynamic system, moving with purpose dictated by physical laws, seasonal cycles, and chemical interactions. In this way, Uranus presents a world both alien and knowable, where chemistry writes a story that extends far beyond the reach of human senses, yet can be understood through careful observation, modeling, and experimentation. Beneath the seemingly tranquil appearance of Uranus, hydrogen sulfide quietly defines much of the planet's chemical character. The troposphere, spanning from the visible cloud tops to depths where pressures exceed tens of bars, hosts H2S alongside methane and minor hydrocarbons in a layered and dynamic system. Convection currents transport warmer parcels of air upward, lifting hydrogen sulfide from deeper regions toward cooler altitudes. As molecules rise, temperatures drop, and a fraction of the gas condenses into ultra-thin, diffuse hazes that subtly influence the planet's infrared and microwave signatures. Despite the extreme cold and low solar energy reaching Uranus, these processes continue uninterrupted, sustaining a complex, stratified atmosphere over millennia. At mid and high latitudes, wind patterns facilitate the horizontal redistribution of hydrogen sulfide. Rapid east-west jets sweep gases along the curvature of the planet, ensuring that chemical concentrations remain relatively uniform across vast regions. Equatorial zones with slower and more stable winds allow for minor accumulation and localized layering, creating subtle variations that spectroscopy can detect. These horizontal and vertical dynamics interact with Uranus' unusual axial tilt, producing seasons of extraordinary length. Each pole remains exposed to either decades of sunlight or darkness, driving slow but significant shifts in the chemical equilibrium of hydrogen sulfide and its photochemically derived compounds. The axial tilt also influences convection patterns, altering the rate at which hydrogen sulfide rises and sinks within the troposphere. During prolonged sunlight, ultraviolet radiation triggers photolysis in the upper layers, breaking down H2S molecules and generating elemental sulfur and trace polysulfides. These particles gradually descend, replenishing lower layers and maintaining overall H2S concentrations. In darkness, photolytic processes pause, allowing hydrogen sulfide to accumulate near the upper troposphere, slowly establishing a different equilibrium until the next prolonged sunlight period. Over decades, this cyclical rhythm creates a temporal layering that is as much a function of time as of altitude or latitude. Spectroscopic detection remains essential for understanding these processes. Infrared wavelengths reveal the presence of hydrogen sulfide in mid to lower troposphere layers, while ultraviolet and radio measurements provide additional insights into temperature, pressure, and molecular interactions. By analyzing absorption features and comparing them to laboratory spectra of H2S under extreme conditions, scientists construct models that predict atmospheric behavior over seasonal cycles. These models account for vertical mixing, horizontal transport, photochemical breakdown, and condensation processes, providing a comprehensive understanding of hydrogen sulfide's persistence and mobility. Temperature and pressure gradients shape the stability of hydrogen sulfide. Near the cloud tops, extreme cold allows minor condensation into faint hazes, while deeper layers with high pressures retain the gas in a gaseous state. This stratification, combined with horizontal redistribution via winds, creates a multi-layered atmospheric profile in which H2S remains significant over long timescales. Methane clouds overlay these layers, contributing to Uranus's characteristic blue-green color and interacting with hydrogen sulfide in ways that subtly affect absorption spectra. The result is a planet whose chemical identity is simultaneously hidden and measurable, understood through indirect observation and scientific inference rather than direct sensory experience. Hydrogen sulfide also informs our understanding of Uranus's formation. The early solar system's protoplanetary disk contains sulfur-rich ices and gases, which became incorporated into the forming ice giant. Accretion concentrated H2S in the outer layers, where it remains today, modified only by convection, diffusion, and photochemistry. Comparing Uranus to Neptune, which formed in a nearby region, highlights small but consequential differences in gas abundance, suggesting that even minute variations in initial conditions or early atmospheric processes can create observable differences in chemical composition between otherwise similar planets. Photochemistry drives slow but ongoing transformation within Uranus's atmosphere. Ultraviolet radiation breaks down hydrogen sulfide in upper layers, forming sulfur atoms and minor compounds that slowly settle toward the troposphere. Methane undergoes similar photochemical reactions, producing ethane, acetylene, and other hydrocarbons that interact with sulfur compounds. This continuous cycle of molecular destruction, recombination, and settling ensures that hydrogen sulfide remains present, contributing to the stability of the chemical profile despite prolonged exposure to radiation and extreme cold. Laboratory simulations on Earth provide crucial insight into these processes. By replicating the low temperatures and high pressures of Uranus's troposphere, scientists observe hydrogen sulfide's physical and chemical behavior in controlled conditions. Experiments confirm that H2S remains gaseous under deep pressures, condenses only under extreme cooling, and participates in slow photochemical reactions when exposed to ultraviolet light. These studies validate atmospheric models, ensuring that predictions of vertical and horizontal gas distribution align with observed data from spectroscopy and past spacecraft measurements. Even without human presence, Uranus's hydrogen sulfide-rich atmosphere conveys a vivid chemical reality. Each molecule participates in a complex dance of convection, diffusion, and photochemistry, moving slowly yet consistently across thousands of kilometers. Winds transport gases horizontally, while vertical gradients and seasonal variations dictate upward and downward flow. Photochemical reactions break and reconstitute molecules, producing faint secondary compounds that gradually settle, sustaining a layered structure rich in H2S. The planet's silent chemistry unfolds on scales of decades and centuries, a continuous process that defines its identity and differentiates it from all other worlds in the solar system. Through careful study, we can appreciate the subtlety and persistence of Uranus's hydrogen sulfide. Though invisible and unreachable, H2S shapes the planet's color, its spectral characteristics, and its layered atmospheric structure. Each molecule, though minuscule, contributes to a larger chemical story that reveals the planet's history, dynamics, and ongoing processes. In this way, the science of hydrogen sulfide provides a tangible connection to an otherwise inaccessible world, allowing us to understand and even imagine its chemical presence, despite the impossibility of direct human experience. Descending further into the depths of Uranus's troposphere, hydrogen sulfide dominates the chemical environment in ways that remain invisible but measurable. The lower layers, subject to pressures exceeding tens of bars, provide a stable environment in which H2S persists in gaseous form despite extreme cold. Convection slowly moves parcels of gas upward, where a fraction of H2S condenses into faint hazes, interacting with methane clouds to form a stratified chemical structure. These layers, imperceptible to optical observation, influence the planet's infrared and microwave spectra, allowing scientists to map their distribution and understand the dynamics of the atmosphere without physical sampling. Wind patterns across Uranus create subtle yet significant redistribution of hydrogen sulfide. High-latitude jets accelerate east-west transport, sweeping gases along thousands of kilometers, while equatorial regions experience slower winds that permit minor accumulations and localized layering. This horizontal mixing complements a vertical convection, ensuring that H2S concentrations remain relatively uniform across wide expanses, while still allowing for minor variations detectable through spectroscopy. The planet's axial tilt further modulates these dynamics, producing prolonged seasons that expose each hemisphere to decades of sunlight or darkness, influencing photochemical reactions and vertical distribution over multi-decade timescales. During prolonged sunlight, ultraviolet radiation initiates photolysis of H2S molecules in the upper layers, breaking them down into elemental sulfur and minor sulfur-bearing compounds. These particles gradually settle toward the lower troposphere, replenishing hydrogen sulfide concentrations and maintaining equilibrium. In the opposite dark seasons, photolytic processes cease, allowing H2S to accumulate higher in the atmosphere, establishing a slow, cyclical chemical layering dictated by Uranus's orbital period and axial orientation. Over decades and centuries, this seasonal rhythm governs the persistence and vertical distribution of sulfur compounds, illustrating the interplay between solar radiation, rotation, and atmospheric chemistry. Spectroscopy provides the primary window into these processes by observing absorption at specific infrared wavelengths. Astronomers identify hydrogen sulfide amidst hydrogen, helium, and methane. Complementary ultraviolet and radio measurements yield additional insights into pressure, temperature, and molecular interactions. Laboratory simulations on Earth validate these observations, demonstrating that H2S remains gaseous under deep tropospheric pressures, condenses only under extreme cooling, and participates in slow photochemical reactions when exposed to ultraviolet light. These combined methods enable a comprehensive understanding of Uranus's chemical environment, despite the impossibility of direct human sampling. Temperature gradients govern the condensation and stability of hydrogen sulfide. Near the cloud tops, extreme cold allows minor condensation into thin hazes, whereas deeper layers under high pressure retain the gas in a stable, gaseous state. Methane clouds form slightly above these H2S layers, creating a vertical structure in which sulfur compounds remain consistently present while interacting chemically with hydrocarbons. This stratified structure is essential to Uranus's spectral identity, producing absorption patterns that reveal the presence of hydrogen sulfide and its layered distribution across tropospheric altitudes. The persistence of hydrogen sulfide reflects the planet's formation history. Uranus accreted from a protoplanetary disk rich in sulfur-bearing compounds, capturing H2S in its outer layers. Over billions of years, the chemical and physical environment, defined by convection, diffusion, and photochemistry, has preserved these molecules in the troposphere. Comparisons with Neptune suggest that slight variations in initial conditions can lead to observable differences in sulfur content, emphasizing the sensitivity of planetary atmospheres to formation history and early chemical processes. Hydrogen sulfide's photochemistry contributes to the ongoing dynamics of Uranus's atmosphere. Ultraviolet radiation breaks down molecules in the upper layers, generating secondary sulfur compounds that settle into lower layers, reinforcing the presence of H2S. Methane photochemistry produces hydrocarbons that interact with sulfur compounds, forming faint hazes that alter absorption properties and contribute to the planet's overall chemical layering. This continuous cycle of molecular breakdown, recombination, and settling maintains the stability of hydrogen sulfide concentrations across the troposphere. Laboratory research reproduces Uranus's extreme conditions, providing critical insight into hydrogen sulfide behavior. By simulating low temperatures and high pressures, scientists observe molecular mobility, condensation points, and chemical interactions with methane and ammonia. Ultraviolet irradiation experiments replicate photochemical processes, confirming that hydrogen sulfide persists despite decomposition in upper layers. These studies validate models of atmospheric structure and dynamics, allowing predictions of H2S distribution and long-term stability under varying seasonal and latitudinal conditions. Even in the absence of direct human experience, the chemical reality of hydrogen sulfide on Uranus is vivid. Each molecule participates in a slow, deliberate cycle, dictated by convection, diffusion, and photochemistry. Winds move gases across latitudes, while vertical gradients and seasonal cycles determine their rise and fall. Photochemical reactions generate secondary compounds, which gradually settle, sustaining a layered atmosphere rich in H2S. The planet's chemistry unfolds over decades and centuries, creating a persistent yet dynamic signature that defines Uranus as a world distinct from all others in the solar system. Through observation, experimentation, and modeling, we gain a clear understanding of Uranus's hydrogen sulfide. Though invisible and inaccessible, the gas defines the planet's atmospheric identity, influencing cloud structure, spectral characteristics, and chemical layering. Each molecule, moving through convection currents, responding to ultraviolet radiation, and interacting with other compounds, contributes to a vast dynamic system. In this way, Uranus's hydrogen sulfide-rich atmosphere tells a story of formation, chemistry, and persistence, a silent yet profound testament to the complexity of worlds beyond our own. Within Uranus's atmosphere, hydrogen sulfide continues to define the chemical and physical character of the planet, silently interacting with other atmospheric constituents. Deeper tropospheric layers, where pressures rise to tens of bars and temperatures remain near -200 degrees Celsius, maintain H2S in gaseous form. Convection currents slowly lift the gas toward cooler upper layers, where a fraction condenses into diffuse, nearly invisible hazes. These layers coexist with methane clouds, creating vertical stratification that is detectable only through infrared spectroscopy. Despite the extreme cold and low solar energy, the slow circulation of gases ensures a stable yet dynamic environment for hydrogen sulfide over decades and centuries. High-latitude jets play a crucial role in redistributing H2S horizontally across the planet. Winds exceeding 800 kilometers per hour carry hydrogen sulfide along curved trajectories dictated by the planet's rotation and axial tilt. In equatorial regions, slower and more stable winds allow localized variations in chemical concentrations, leading to subtle differences in gas layering. Seasonal shifts, dictated by Uranus's extreme axial tilt, modulate these circulation patterns, exposing each hemisphere to prolonged sunlight or darkness for approximately 42 years at a time. These extended seasons influence photochemical reactions and vertical transport, slowly reshaping hydrogen sulfide distribution over decades. During periods of prolonged sunlight, ultraviolet radiation induces photolysis in upper tropospheric H2S, breaking molecules into elemental sulfur and minor sulfur-bearing compounds. These secondary particles gradually settle toward lower layers, replenishing hydrogen sulfide and contributing to a self-sustaining chemical cycle. In dark seasons, photolytic processes pause, allowing H2S to accumulate in higher atmospheric layers, creating a cyclical pattern of chemical layering governed by Uranus's orbital period. Over centuries, this slow rhythm maintains the persistence and equilibrium of hydrogen sulfide in the troposphere. Remote sensing via spectroscopy provides the primary means of studying hydrogen sulfide. Infrared measurements identify H2S absorption features in mid and lower troposphere layers, while ultraviolet and radio data reveal complementary information about pressure, temperature, and molecular interactions. Laboratory simulations on Earth, replicating Uranus's low temperatures and high pressures, validate these observations. Experiments confirm that hydrogen sulfide remains gaseous under deep pressures, condenses under extreme cooling, and participates in slow photochemical reactions when exposed to ultraviolet light. These techniques together provide a detailed picture of the gas's distribution, behavior, and persistence. Temperature gradients within Uranus's atmosphere dictate the condensation and stability of hydrogen sulfide. Upper layers, subjected to extreme cold, permit minor condensation into thin hazes, while deeper layers retain H2S in gaseous form. Methane clouds form slightly above these layers, producing vertical stratification that contributes to spectral characteristics detectable across interplanetary distances. Horizontal winds, vertical convection, and seasonal variations combine to maintain this stratified chemical structure, allowing hydrogen sulfide to persist over decades and centuries with minimal disruption. Hydrogen sulfide also illuminates aspects of Uranus's formation. The planet accreted in a region of the protoplanetary disk rich in sulfur-bearing compounds. Accretion concentrated H2S in the outer layers, where it has remained, modified only by convection, diffusion, and photochemistry. Comparisons with Neptune, formed in a similar region, indicate that even minor differences in initial conditions produce measurable variations in upper atmospheric hydrogen sulfide, highlighting the sensitivity of planetary chemistry to formation and evolutionary factors. Photochemical reactions continuously reshape hydrogen sulfide within Uranus's atmosphere. Ultraviolet radiation decomposes H2S in upper layers, producing secondary sulfur compounds that settle into lower layers. Methane undergoes parallel reactions, creating ethane and other hydrocarbons that interact with sulfur compounds, forming faint hazes detectable via infrared spectroscopy. This continuous cycle of molecular breakdown, recombination, and deposition preserves hydrogen sulfide concentrations and maintains the layered chemical equilibrium of the atmosphere. Laboratory studies reinforce our understanding of these processes. Scientists simulate low-temperature, high-pressure conditions to observe H2S behavior, including molecular mobility, condensation, and chemical interactions with methane and ammonia. Ultraviolet irradiation experiments replicate photochemical processes, confirming that hydrogen sulfide persists despite ongoing decomposition in upper layers. By combining laboratory data with remote sensing observations, researchers construct reliable models of Uranus's atmospheric dynamics, accurately predicting hydrogen sulfide distribution across vertical and horizontal layers. Even in the absence of direct sensory experience, the presence of hydrogen sulfide defines Uranus's chemical identity. Each molecule participates in convection-driven circulation, horizontal transport, and photochemical cycling. Winds move gases across latitudes, while vertical gradients and seasonal cycles control ascent and descent. Secondary compounds settle slowly, reinforcing layered structures. Over decades and centuries, this subtle, continuous chemical activity gives Uranus its persistent yet dynamic atmospheric character, distinct from all other planets in the solar system. Through observation, modeling, and experimentation, scientists gain a detailed understanding of hydrogen sulfide. Invisible yet measurable, each molecule contributes to cloud structure, spectral absorption, and atmospheric layering. The gas moves in concert with planetary rotation, responds to ultraviolet radiation, and interacts chemically with other molecules, creating a vast, slowly evolving system. In this way, hydrogen sulfide on Uranus tells a story of persistence, chemical complexity, and planetary identity, offering a rare glimpse into the silent, ongoing processes that define worlds far from our own. Hydrogen sulfide in Uranus's atmosphere is not only a chemical constituent, but a tracer of the planet's dynamic and physical processes. In the mid and lower troposphere, where pressures are substantial and temperatures are low, H2S remains largely gaseous, participating in a slow, methodical circulation driven by convection currents. Warm air from the interior rises, carrying hydrogen sulfide toward cooler upper layers, where partial condensation forms ultra-thin hazes. These faint layers coexist with methane clouds, producing stratification that affects the planet's infrared and microwave absorption characteristics. Through careful spectroscopic analysis, scientists can discern the presence, concentration, and vertical distribution of H2S, revealing the hidden architecture of Uranus's atmospheric chemistry. The planet's winds facilitate horizontal redistribution of hydrogen sulfide across vast distances. High-latitude jets move gases at hundreds of kilometers per hour, while equatorial zones allow slower, more localized accumulation. These patterns interact with Uranus's extreme axial tilt, which creates decades-long seasons that expose each hemisphere alternately to extended sunlight or prolonged darkness. Sunlit periods drive photolytic reactions in the upper atmosphere, breaking H2S molecules into sulfur and minor compounds that gradually settle to lower layers. During the long dark season, these reactions halt, permitting H2S to accumulate at higher altitudes, establishing a cyclical vertical distribution governed by the planet's orbital and rotational characteristics. Photochemistry is central to the persistence of hydrogen sulfide. Ultraviolet radiation decomposes molecules in upper layers, generating sulfur compounds that descend, replenishing lower atmospheric levels. Simultaneously, methane and trace hydrocarbons undergo reactions producing ethane and acetylene, which interact with sulfur compounds to form faint hazes detectable via infrared spectroscopy. This ongoing cycle of decomposition, recombination, and deposition maintains equilibrium, ensuring H2S remains a dominant feature of the troposphere despite continuous exposure to radiation and extreme cold. Laboratory experiments on Earth replicate these extraterrestrial conditions, providing direct insight into H2S behavior. Low temperature, high pressure simulations demonstrate the gas's mobility, condensation thresholds, and chemical interactions with methane and ammonia. Ultraviolet irradiation reproduces photochemical processes observed on Uranus, confirming that hydrogen sulfide persists over extended periods even as upper layer molecules break down. These studies validate atmospheric models, enabling precise predictions of vertical and horizontal gas distributions across different latitudes and seasonal conditions. Temperature gradients and pressure profiles within Uranus's atmosphere define the behavior and stability of hydrogen sulfide. In upper layers, extreme cold allows minor condensation into diffuse hazes, while deeper layers maintain the gas in a stable, gaseous form. Methane clouds overlay these regions, contributing to the characteristic blue-green coloration and interacting chemically with H2S in ways that influence absorption features. Horizontal winds, vertical convection, and seasonal shifts ensure a dynamic yet stable stratification, allowing hydrogen sulfide to persist for decades, centuries, and potentially millennia. The presence of H2S reflects Uranus's formative environment. During planetary accretion, the protoplanetary disk supplied sulfur-rich ices and gases, which became concentrated in the planet's outer layers. Over billions of years, atmospheric dynamics, including convection, diffusion, and photochemistry, have maintained hydrogen sulfide in the troposphere. Comparative studies with Neptune indicate that minor differences in initial conditions produce measurable disparities in hydrogen sulfide abundance, illustrating the sensitivity of ice giant atmospheres to formation and early evolutionary processes. Observations reveal the intricate balance of chemistry, physics, and motion that sustains hydrogen sulfide. Despite its invisibility, H2S contributes to the planet's spectral identity, interacting with other gases to create a layered, structured atmosphere. Its movement is governed by slow convection, horizontal winds, and seasonal cycles, while photochemical reactions produce secondary compounds that descend gradually, reinforcing the chemical structure. Over decades and centuries, these processes maintain equilibrium, highlighting the persistence of chemical patterns across immense scales. Spectroscopy allows scientists to reconstruct this hidden world. Infrared absorption lines pinpoint hydrogen sulfide's presence at specific altitudes, while ultraviolet and radio measurements provide complementary insights into temperature, pressure, and molecular interactions. The combination of remote sensing and laboratory validation allows researchers to model Uranus's atmosphere accurately, predicting H2S behavior under varying seasonal and latitudinal conditions. Each spectral measurement confirms that hydrogen sulfide is both persistent and dynamic, a defining component of the planet's atmospheric chemistry. Even without direct human experience, hydrogen sulfide defines Uranus's chemical identity. Each molecule participates in a delicate cycle of convection, horizontal transport, and photochemistry. Winds distribute gases across thousands of kilometers. Vertical gradients govern rise and descent, and photochemical reactions continually regenerate sulfur compounds. These processes create a persistent, layered atmosphere that evolves slowly over decades and centuries, defining Uranus as chemically unique among the solar system's planets. Through careful observation, laboratory study, and modeling, we can appreciate hydrogen sulfide's role in shaping Uranus's atmosphere. Invisible yet measurable, each molecule contributes to spectral characteristics, cloud formation, and chemical layering. The slow, methodical dynamics of H2S offer a glimpse into the processes that sustain a chemically complex environment far from the Sun. Uranus's atmosphere, rich in hydrogen sulfide, stands as a testament to the interplay of physics and chemistry, revealing the subtle, persistent mechanisms that govern planetary worlds beyond our reach. As hydrogen sulfide continues its slow circulation within Uranus's atmosphere, the subtle interplay between pressure, temperature, and chemical reactions becomes increasingly evident. In the lower troposphere, where pressure rises to several tens of bars, H2S remains a stable gas, unaffected by the coldest temperatures that dominate the upper layers. Convection carries parcels of hydrogen sulfide upward, and although only a tiny fraction condenses into faint, nearly invisible hazes, this process contributes to the layered structure of the atmosphere. Methane clouds, forming slightly higher, overlap with these hazes, creating a stratified system that shapes the planet's spectral absorption in the infrared and microwave bands. Horizontal redistribution, facilitated by wind patterns, ensures that hydrogen sulfide is dispersed across wide expanses. At high latitudes, winds can exceed 900 kilometers per hour, rapidly transporting gases along curved trajectories defined by the planet's rotation and axial tilt. Equatorial regions experience slower winds, allowing minor variations and localized layering. Seasonal shifts caused by Uranus's extreme axial tilt expose each hemisphere to extended periods of sunlight or darkness, driving slow cycles of photochemical breakdown in upper layers. During sunlight, ultraviolet radiation decomposes H2S into elemental sulfur and minor compounds that gradually settle to lower layers. In darkness, these reactions cease, permitting H2S to accumulate higher in the atmosphere, creating a cyclical vertical distribution over decades. The chemical equilibrium of hydrogen sulfide is further influenced by photochemical interactions with methane and trace hydrocarbons. Methane, when exposed to ultraviolet radiation, generates ethane and acetylene, which can interact with sulfur compounds to form faint hazes. These hazes are dispersed throughout the atmosphere, altering absorption spectra while contributing to the planet's complex chemical layering. The continuous cycle of decomposition, recombination, and sedimentation preserves H2S concentrations and maintains atmospheric stability, even under extreme environmental conditions. Temperature gradients in Uranus's troposphere play a crucial role in hydrogen sulfide behavior. Upper layers, near the cloud tops, are extremely cold, allowing partial condensation of H2S into ultra-thin hazes. Deeper layers, subjected to high pressure, retain the gas in a stable gaseous state. This stratification, combined with horizontal wind patterns and slow seasonal shifts, creates a dynamic yet persistent atmosphere where hydrogen sulfide remains present over decades, centuries, and even millennia. Methane clouds overlay these H2S layers, contributing to Uranus's characteristic blue-green hue and interacting chemically to influence spectral characteristics. The formation history of Uranus is reflected in its hydrogen sulfide-rich atmosphere. During planetary accretion, sulfur-bearing compounds in the protoplanetary disk were incorporated into the planet's outer layers. Over billions of years, convection, diffusion, and photochemistry have preserved H2S in the troposphere. Comparisons with Neptune indicate that even minor variations in initial conditions or early atmospheric processes can produce measurable differences in sulfur content, highlighting the sensitivity of ice giant atmospheres to formation and early evolution. Hydrogen sulfide's photochemistry is slow yet persistent. Ultraviolet radiation decomposes molecules in upper layers, producing secondary sulfur compounds that settle toward lower layers. Simultaneously, methane photochemistry generates hydrocarbons that interact with sulfur compounds, forming faint hazes detectable via infrared spectroscopy. These processes ensure that hydrogen sulfide remains a dominant feature of the atmosphere, maintaining a layered structure that reflects both seasonal and long-term chemical cycles. Laboratory simulations continue to validate our understanding of H2S behavior. Experiments replicate the low temperatures and high pressures of Uranus's troposphere, observing gas mobility, condensation points, and chemical interactions with methane and ammonia. Ultraviolet irradiation reproduces photochemical reactions, confirming that hydrogen sulfide persists over long periods despite ongoing decomposition in upper layers. These findings support atmospheric models, providing a detailed picture of vertical and horizontal distribution, seasonal variation, and long-term stability. Even though hydrogen sulfide is invisible and unreachable, it defines Uranus's chemical identity. Each molecule moves within convection currents, responds to seasonal and photochemical influences, and interacts with other gases to maintain a stratified, persistent atmosphere. Horizontal winds distribute H2S across latitudes, while vertical gradients govern rise and descent. Secondary compounds created by photochemistry settle slowly, contributing to a stable yet dynamic chemical environment. Over decades, centuries, and longer, these processes preserve the unique chemical signature of Uranus. In this way, the slow, methodical movement of hydrogen sulfide forms the invisible framework of the planet's atmosphere. Its presence is a testament to the interplay of chemistry, physics, and planetary dynamics, revealing a world that is chemically complex yet profoundly silent. Observations and models provide a glimpse into this hidden system, showing how invisible molecules shape the structure, stability, and identity of an entire planet. Hydrogen sulfide, in its persistent yet subtle ways, governs the chemical rhythm of Uranus, offering a rare and detailed understanding of atmospheric processes in an environment far removed from human experience. Deeper within Uranus's atmosphere, hydrogen sulfide interacts with subtle variations in temperature, pressure, and chemical composition to maintain its persistent presence. In the lower troposphere, pressures exceed tens of bars and temperatures remain around -200 degrees Celsius. Here, H2S exists almost entirely in gaseous form, while convection currents slowly transport parcels of gas toward upper layers. A fraction of these molecules condenses into faint, diffuse hazes that intermingle with methane clouds. These overlapping layers form a stratified structure, creating a complex vertical profile that shapes the planet's spectral characteristics, particularly in the infrared and microwave wavelengths. The faint hazes and cloud layers, though invisible to the eye, reveal the underlying chemical architecture of Uranus when analyzed through careful spectroscopy. Horizontal transport is equally critical in distributing hydrogen sulfide. High-latitude winds, reaching speeds of 800 to 900 kilometers per hour, sweep gases around the planet, ensuring that concentrations remain relatively uniform across vast regions. In equatorial zones, winds are slower, permitting localized variations and minor accumulation of H2S. Uranus' extreme axial tilt introduces prolonged seasonal effects, with each hemisphere experiencing 42-year-long periods of sunlight or darkness. Sunlight drives photochemical reactions in upper layers, breaking down hydrogen sulfide into sulfur and minor compounds, which gradually settle into lower atmospheric layers. During extended darkness, photolysis halts, allowing H2S to accumulate at higher altitudes, establishing slow, cyclical variations in vertical distribution. Photochemistry continues to transform hydrogen sulfide subtly but persistently. Ultraviolet radiation decomposes molecules in the upper troposphere, producing sulfur atoms and minor compounds that settle over time. Methane undergoes similar reactions, generating ethane, acetylene, and other hydrocarbons that can interact with sulfur compounds, forming faint, invisible hazes detectable through infrared observation. This ongoing cycle of decomposition, recombination, and sedimentation preserves hydrogen sulfide levels, maintaining the chemical layering and equilibrium that defines Uranus's atmosphere. Temperature and pressure gradients shape the condensation and mobility of hydrogen sulfide. In upper layers, the extreme cold allows for partial condensation into faint, thin hazes. Deeper layers maintain the gas in a stable, gaseous state due to the high pressures. Methane clouds form above these layers, creating a vertical stratification that influences both the planet's coloration and its absorption spectra. Horizontal winds, vertical convection, and seasonal cycles interact seamlessly, maintaining the stability of hydrogen sulfide over extensive timescales. The delicate balance of these processes ensures a persistent chemical environment resistant to disruption despite Uranus's extreme and slowly changing conditions. Hydrogen sulfide also provides insight into Uranus's early formation. During the accretion phase, sulfur-bearing compounds in the protoplanetary disk were captured in the planet's outer layers. Over billions of years, convection, diffusion, and photochemical processes have maintained hydrogen sulfide in the troposphere. Comparing Uranus with Neptune, formed in a similar region, reveals how even slight differences in initial conditions produce measurable variations in H2S concentration. This comparison underscores the sensitivity of ice giant atmospheres to formation history, chemical environment, and long-term evolutionary factors. Laboratory simulations replicate these extreme conditions, providing detailed observations of H2S behavior. Experiments at low temperatures and high pressures confirm that hydrogen sulfide remains gaseous in the lower atmosphere, condenses under extreme cooling, and undergoes slow photochemical reactions when exposed to ultraviolet light. These experiments validate remote sensing data, ensuring atmospheric models accurately predict vertical and horizontal distributions, seasonal variations, and long-term stability. By bridging the gap between observation and theory, laboratory studies illuminate the continuous chemical processes that define Uranus's troposphere. Even though humans cannot directly observe or smell hydrogen sulfide, its presence is fundamental to Uranus's atmospheric identity. Each molecule circulates through convection currents, responds to seasonal light cycles, and participates in photochemical reactions that generate secondary sulfur compounds. Horizontal and vertical transport ensures widespread distribution, while settling particles reinforce stratification. Over decades, centuries, and longer, these processes maintain a layered, persistent atmosphere where hydrogen sulfide dominates the chemical landscape. The continuous, methodical dynamics of hydrogen sulfide demonstrate the interplay of physics, chemistry, and planetary mechanics. The gas quietly defines Uranus's character, shaping its cloud structures, spectral absorption, and overall atmospheric composition. Observational data, laboratory experiments, and theoretical models converge to reveal an environment that is complex, persistent, and silently dynamic. Hydrogen sulfide is both the signature and the framework of Uranus's atmosphere, governing its chemical rhythm in a world far removed from human experience, yet fully comprehensible through scientific inquiry. As we consider the vastness of Uranus's atmosphere, it is remarkable how a single molecule type, hydrogen sulfide, can dominate chemical processes across thousands of kilometers and billions of years. The intricate dance of condensation, convection, photochemistry, and diffusion ensures that the planet remains chemically stable while slowly evolving over time. Each molecule participates in a system far larger than itself, creating patterns of persistence, layering, and chemical transformation that define the ice giant in ways invisible yet measurable from afar. The persistence of hydrogen sulfide in Uranus's atmosphere also illustrates the delicate balance between chemical stability and dynamic circulation. As parcels of gas rise through convection currents, the gradual decrease in temperature allows only a minor portion of H2S to condense into faint, nearly invisible hazes. These thin layers interact with overlying methane clouds, producing a stratified system that influences the absorption of infrared radiation, enabling scientists to detect and quantify hydrogen sulfide remotely. The continual, slow motion of gases ensures that even in the coldest regions, the overall distribution of H2S remains relatively uniform, though minor variations emerge in equatorial regions where winds are less vigorous. Seasonal changes, governed by Uranus' extreme axial tilt, induce long-term cycles in hydrogen sulfide distribution. Prolonged sunlight triggers photolysis in the upper troposphere, decomposing H2S into elemental sulfur and minor sulfur compounds. Over time, these products settle to lower layers, replenishing the troposphere and sustaining the overall chemical equilibrium. Conversely, during decades-long darkness, photochemical processes halt, allowing H2S to accumulate at higher altitudes. These cyclical variations create subtle vertical layering that persists over decades and centuries, reflecting both seasonal and long-term atmospheric dynamics. Photochemical interactions between hydrogen sulfide and other gases, such as methane, ethane, and acetylene, further define the structure and composition of Uranus's atmosphere. Methane, exposed to ultraviolet light, forms hydrocarbons that interact with sulfur compounds, producing faint hazes that are detectable via infrared spectroscopy. The slow, continuous cycle of decomposition, recombination, and settling ensures that hydrogen sulfide remains a dominant chemical component. This chemical interplay, though invisible, maintains a structured and resilient atmosphere, allowing H2S to persist even under extreme environmental conditions. Temperature and pressure gradients within the troposphere regulate the behavior of hydrogen sulfide. The upper layers, subjected to extreme cold, permit minor condensation, forming thin hazes that coexist with methane clouds. Deeper regions, under high pressure, retain H2S in gaseous form. The combination of vertical convection, horizontal winds, and seasonal variation creates a multi-layered atmosphere where hydrogen sulfide remains stable over extensive timescales. The interaction of H2S with methane clouds subtly influences the planet's blue-green coloration and contributes to the specific spectral signatures used to detect the gas. The presence of hydrogen sulfide also informs our understanding of Uranus formation. During the accumulation of the planet, sulfur-rich ices and gases were incorporated into the outer layers, creating the chemical foundation for today's troposphere. Over billions of years, atmospheric dynamics, convection, diffusion, and photochemistry have maintained H2S in gaseous form. Comparisons with Neptune reveal that slight differences in initial conditions can result in measurable differences in sulfur content, illustrating the sensitivity of planetary atmospheres to formation history and chemical environment. Laboratory simulations provide crucial insight into hydrogen sulfide's behavior under extraterrestrial conditions. Low temperature, high pressure experiments demonstrate the gas's condensation points, molecular mobility, and chemical interactions with methane and ammonia. Ultraviolet irradiation replicates photochemical reactions observed on Uranus, confirming that H2S persists over long periods, even as upper layer molecules break down. These studies corroborate remote sensing data and theoretical models, ensuring a comprehensive understanding of vertical and horizontal distribution, seasonal variation, and long-term stability. Despite its invisibility, hydrogen sulfide defines Uranus's atmospheric identity. Each molecule participates in convection-driven circulation, horizontal transport, and photochemical cycles. Winds distribute H2S across thousands of kilometers. Vertical gradients dictate ascent and descent, and secondary compounds produced by photochemistry settle slowly, reinforcing stratification. Over decades, centuries, and longer, these processes maintain a layered, persistent atmosphere dominated by hydrogen sulfide, making it a defining feature of the planet. The silent, methodical movements of hydrogen sulfide illustrate the intersection of physics, chemistry, and planetary dynamics. Each molecule contributes to cloud structures, absorption patterns, and chemical layering, forming a resilient yet dynamic atmosphere. The subtle interplay of convection, wind, photochemistry, and seasonal cycles creates a planet that is chemically rich and structurally stable. Hydrogen sulfide, in its persistence and subtlety, governs the chemical rhythm of Uranus, revealing a world far from the Sun where invisible molecules shape an entire planetary environment. Even in the absence of human senses, the presence of hydrogen sulfide tells a story of endurance, adaptation, and chemical complexity. The gas circulates slowly through convection currents, responds to ultraviolet light, interacts with other molecules, and settles to form faint hazes, all while maintaining its integral role in the atmosphere. Across decades and centuries, these processes create a quiet, dynamic equilibrium that defines Uranus chemically, providing insight into the invisible yet powerful forces that shape ice giants in our solar system. As the layers of hydrogen sulfide settle into a slow, persistent rhythm, the full complexity of Uranus's atmosphere becomes apparent. Each molecule participates in a continuous cycle, rising in convection currents, dispersing along powerful high-latitude winds, interacting chemically with methane and trace hydrocarbons, undergoing slow photolytic decomposition under prolonged sunlight, and gradually settling into lower layers. This process, invisible to the human eye, maintains a delicate equilibrium that has endured for billions of years. The interplay of physical forces and chemical reactions forms a dynamic yet stable system where hydrogen sulfide defines the structure, composition, and spectral identity of the planet. Seasonal variations continue to influence the chemical layering of H2S. During sunlight-exposed decades, ultraviolet radiation breaks down upper layer hydrogen sulfide into elemental sulfur and minor sulfur compounds. These secondary products slowly descend, replenishing the lower troposphere and maintaining overall chemical balance. In the opposite hemisphere, experiencing decades of darkness, photochemical processes pause, allowing H2S to accumulate in upper layers. These long-term cycles of chemical transformation and redistribution create subtle, multi-layered vertical structures, demonstrating how Uranus' extreme axial tilt orchestrates slow yet profound chemical rhythms over decades and centuries. The interaction between hydrogen sulfide and methane is another defining characteristic of Uranus's atmosphere. Methane clouds overlay the H2S layers, influencing the planet's blue-green hue and interacting chemically with sulfur compounds. Photochemically generated hydrocarbons including ethane and acetylene, form faint, diffuse hazes that subtly modify the absorption spectra, offering scientists measurable evidence of chemical layering. These interactions highlight the intricate relationships among different gases, showing how even invisible molecules collectively define the observable characteristics of the planet. Laboratory simulations reinforce these observations, providing controlled insight into H2S behavior. Low temperature, high pressure experiments replicate conditions in the lower and middle troposphere, revealing the gas's mobility, condensation thresholds, and chemical interactions. Ultraviolet irradiation reproduces photochemical processes observed on Uranus, confirming that hydrogen sulfide persists over extended periods, even as some molecules decompose in upper layers. By combining these experimental results with spectroscopic data and atmospheric models, scientists can map H2S distribution accurately, predict seasonal variations, and understand long-term atmospheric stability. Despite its invisibility and inaccessibility, hydrogen sulfide shapes Uranus's chemical identity, each molecule moving through convection, dispersing along winds, interacting chemically, and settling gradually, contributes to a stable yet dynamic system. The gas defines cloud, structures, spectral features, and layered atmospheric organization. Over decades, centuries, and longer, hydrogen sulfide remains a constant presence, silently orchestrating the chemical and physical rhythms of the planet, making Uranus chemically distinct among the ice giants. Reflecting on these processes, one can appreciate the subtle power of hydrogen sulfide. Though imperceptible to human senses, it organizes an entire atmosphere, balancing motion, chemistry, and solar influence. The slow, methodical transformations occurring within Uranus's troposphere exemplify the delicate harmony of planetary systems, where even the smallest molecules can dictate structure, appearance, and chemical identity. Hydrogen sulfide's persistence and subtlety provide a profound insight into the hidden forces shaping worlds far from the Sun. As the planet continues its silent, ceaseless chemical dance, hydrogen sulfide remains central, an unseen architect of atmospheric complexity. Its interactions, movements, and transformations persist across millennia, shaping the spectral, physical, and chemical reality of Uranus. For observers on Earth, the presence of H2S offers a tangible connection to this distant, frozen world, a window into the invisible but enduring processes that govern ice giant atmospheres. And so, in the quiet expanse of space, hydrogen sulfide defines Uranus. Invisible, silent, yet persistent, it moves slowly but decisively through the layers of the atmosphere, shaping, stabilizing, and revealing the intricate chemistry of an ice giant far from human reach. Its story is one of balance, persistence, and chemical resilience, a narrative unfolding over billions of years, quietly sculpting the identity of a planet that has captivated scientists and astronomers alike.